Good morning, Michael. What are we
Morning,
up to
Matt.
today?
Well, I was thinking we should talk a little bit about how to combine derivatives.
Oh, let's look at that.
We've been computing a bunch of simple examples, but how about if we have several functions together, and how will we combine them? Maybe I'll say
IVES.
derivatives. How about that?
Yeah, that's okay. Good.
So rather than doing general formulas and stuff, I was thinking, why don't we start off with a couple of easy examples where we've seen, okay, so like x to the n, what do we know for its derivative? We've worked this out, right?
We worked it out. It's nx to the n minus 1.
So this is the function. And this is the derivative. I'm just trying to be a little bit organized here. I'll give you another nice example. We worked with trig functions. Sine x, when you differentiate it, what do you get?
Cosine x.
Okay. Now the question is, what happens if we add two functions? Something like this, x to the n plus sine x. It's going to have a derivative. I'm not going to tell you what it is, but we'll figure it out.
Oh, okay.
How do you think we should figure it out?
Well, it looks like we can approximate this piece independent of that piece because it's a plus sign here. So we know what this is, and we know how that works out. So I'm going to guess that when you do this, you just get the sum of the right-hand side.
That's exactly right. And in fact, let's do what you said. How do we approximate? So you take x and add a small amount, I'll call it h, and you put it to the n. And then you take sine x and add a small amount to x. And then you approximate both of them. So the first guy, do you remember how our approximation works? So if we have x plus h to the n.
Well, there's x to the n is the leading approximation, and we did this by looking at general polynomials. And then the next one is going to have x to the n minus 1 with an h in it.
Yeah. So this is where the derivative showed up. And this is multiplied by h, right?
Yeah, so
That's our
there's our
approximation.
slope times little bits. So there's our linear approximation, and this square in the square brackets is our derivative.
That's right. So that's the first guy. The second approximation is sine. So again, it's kind of like this. We're going to get a sine x. And then we get a linear term with h here. And what goes here?
That goes there.
That's right. So cosine of x.
So good practice, Michael, because here again we see the coefficient in front of h is what we want.
Right. So now, because we're trying to find out the approximation to this whole thing, let's bring these two guys together. Here's the x to the n, sine x. So this gives me, x to the n plus sine x. That's the function. And then there's the derivative part. So all the stuff that have an h in it, that's this guy. And then this guy. So where's my slope?
Right here between these two round brackets.
And so that's the slope. So that's what we call the derivative.
And so we can see that if this was f of x and this was g of x, the process would be exactly the same. And we would have f of x plus g of x.
Right, so here I'll write down my example. And you see, just like you said, derivative of the first guy plus derivative times the second guy. Derivative of the second guy.
And adding the derivatives together.
Right.
So we're saying the derivative of the sum is the sum of the derivatives.
That's right.
Okay, this is great, but the next one we like to look at, and this is important, is multiplication of functions.
Okay, so you know what? Why do we do multiplication? So I'm going to squeeze this little here. I'm going to multiply these two guys. And let's see what we get. And we've got some of our calculations already. This multiplication, this addition here, multiply.
Oh, maybe you should put a dot.
How about dot? Yeah, that's too much like an X, right?
Yeah,
I'll
put in a
great
dot.
big dot.
Oh, now we're just gonna,
Approximations are the same, so I just put a big dot here.
and it's really only the last line that changes now.
So what happens here, I get x to the n times sine x, so I can put a little dot here. Then in here, I have to put things that are going to have an h term. So this h term times this times this. Huh, that's a little bit different than what I had here. So I've got,
I think you'll have to erase all
I'll
that
have to
because it's
erase.
getting quite long. But,
so
yeah,
I do have this times sine x.
and the other one is going to be x to the n.
Times cos x. And
Not
there's
all
a big
times
h
h.
there.
Oh,
I
the
hope we
h, you
see
can
that.
hardly see that h.
Can we see the h? Oh, on our screen, not quite. So I'm going to just squeeze things in here. Plus x to the n
Cosine
cosine of x
times
all times
h.
h.
And this
Is there
whole
anything
thing
else?
is, just wait, before anything else, there's the slope now, but there's a term that has the product with h squared in it.
Right, so there's an h squared, and I could write it out, but you know what? I don't really care because whatever it is, that's quadratic. And when we do the slope, we only worry about the h term, right?
Yeah, and if this is too big, if h isn't small enough, we'll just make it smaller. Eventually, in what we're doing, h will be small enough so we can neglect that term.
Yeah, to make that concrete, like we're thinking of h as being something like 1 over a million. H squared is 1 over a million times a million, which is a true 1 over a trillion. Very, very tiny.
Very tiny. So that's it. We're done. And in
So what
fact,
goes here?
Well, the same thing. The order of h squared. Oh, there we go. Oh, you're filling that in. Okay.
Yeah, I want to fill in this. So the derivative of the first guy times the second guy plus the first guy.
Times the derivative of the second guy, which is exactly what we have here. And then again, we follow the patterns. We just put f of x times g of x and follow exactly the same process. And so then it's true for the multiplication of any two functions for which they're smooth enough so this approximation is good enough.
So that's exactly right. So now we know how to take derivatives for additions of things and multiplication of things.
Sounds great.
Good enough
Let's
for
go
today.
forward. Yes.
Thanks, Matt.